Forced oscillation. Forced oscillation. When a body capable of oscillation is subjected to an external periodic force, it begins to oscillate under the action of the applied force. In the beginning, the body tries to oscillate with its natural frequency, while the external force tries to impose its own frequency upon the body. Thus, there is a sort of tussle between the driver external force and the body, during which the amplitude of oscillations rises and falls irregularly a number of times. This is transient effect which soon end away. Finally, the body yields to the external force and oscillates with constant amplitude and phase and with the frequency of the force. Its oscillations are then known as forced oscillations. The oscillating body is called driven harmonic oscillator and the external force is called driving force. Now let's see the equation of forced oscillation. Let us consider a system oscillating about an equilibrium position under an external periodic force. Let x be its displacement. X be displacement from the equilibrium position at any instant during the oscillation. Its instantaneous velocity is dx by dt, instantaneous velocity. The force acting upon the system at this instant are: first, a restoring force proportional to the displacement but acting in the opposite direction. A restoring force proportional to the displacement but acting in the opposite direction, that is Fs equals to minus Kx, where K is a force constant and this restoring force is given by this value. Second, a frictional or damping force proportional to the velocity but acting in opposite direction, and this can be written as Fd equals to minus B dx by dt, because it is proportional to velocity. And third one is an external periodic force represented by, third is an external periodic force represented by Fp equals to F naught sine P into T. where F naught is the maximum value of this force. Here F naught is the maximum value of this force, and P is its angular frequency. Here P represent angular frequency. So the total force F acting upon the system is given by F equals to Fs plus Fd plus Fp equals to minus Kx minus B dx by dt plus F naught sin pt. So, and this is equal to the mass into acceleration. So this imply m d2x by dt square equals to minus kx minus b dx by dt plus f naught sin pt. Now this can be arranged as, or arranging this or conveniently, d2x by dt square plus b by m dx by dt plus k by m into x equals to f naught by m sin pt. And now, so here if we take b by m as 2r, k by m as omega square, and f naught by m as f naught, and using this in above equation we get d2x by dt square plus 2r dx by dt plus omega square x equals to f naught sin pt. So this is the forced this is the equation for forced oscillation, and it is a differential equation of motion of forced harmonic oscillator. Now once the transient effect ends away and a steady state is set up, the system will oscillate with the frequency of the applied force. This is a necessary physical condition of the oscillations. Now consider a equation as a solution of this equation, that is, consider this equation is 1. So solution of this equation as x equals to a sin pt minus phi. This is equation 2, where a and phi are arbitrary constants. A and phi are arbitrary constant. A phi arbitrary constants. Now differentiating equation 2 with respect to t twice, we get dx by dt as p into a cos pt minus phi and d2x by dt square, d2x by dt square as minus p square sin minus p square a sin pt minus phi. So now substituting these three values, that is x dx by dt and d2x by dt square, in equation 1, we get minus of d2x by dt square minus p square a sin pt minus phi plus 2r, and dx by dt is ps cos pt minus phi and plus omega square and the value of x is a sin pt minus phi. A sin pt minus phi equals to f naught sin pt, and this is equation Now consider, arrange this equation like or we can write, or this will be, take this value at one place, this and this. So we have a into omega square minus p square sin pt minus phi and plus 2r t into a cos pt minus phi equals to